Welcome to this session on the science of learning. First, before we begin the session, take a moment to introduce yourself to your nearest neighbor. We hope that you will be able to work in small groups throughout the rest of the course. Pause the video here and share with your neighbor your name, discipline, and motivation for taking this course. Welcome back. Throughout the course, we will periodically ask you to pause the video and complete a short activity. It is important that you do these activities because they will help you better understand the concepts we're covering in the course. Let's try this out. We would like you to watch this short video before we continue. Pause the video here and follow the link on this slide to watch a short video. In the whodunit video you just watched, did you notice any of the changes in the room prior to the section in the video when they were being revealed? If you did not, you're not alone. It is hard to notice things that we are not aware of. This video illustrates in many ways some of the ideas we will discuss during today's session. Learning depends on what the learner already knows and the context in which learning takes place. New views of the learning process have emerged from cognition research. Our understanding on the nature and context of learning have indicated a shift from a teacher-centered to a student-centered education. These research findings have a huge implication for how we teach and, more importantly, what we ask our students to do. The goal of this session is to use research on learning and cognition to inform classroom practices and teaching. During this session, we will look at some key research findings from a large body of literature and discuss how they can be translated into classroom practices. The research findings we will cover in this session will continue to reappear throughout the course. We will demonstrate how they inform the way we teach and also the way we designed our courses, lectures, instructional activities, and assignments. In most disciplines, we begin by determining what research has found out about the topic of interest. Then, we use the known research findings to inform our approach. Our personal experiences as learners can sometimes give us the false sense that we know how our students learn. In this course, we will take a different approach to teaching. First, we will discuss what is known about how students learn, and then we will work to implement these findings in all aspects of teaching and course design. The learning objectives for this session are that by the end of the session, you should be able to explain current theories of learning and cognition that explain how students learn, apply cognition and learning research to improve students' learning in your teaching, implement strategies that allow you to reflect on your teaching and evaluate whether or not you're being effective. This lesson will be organized into two parts. During the first part of the session, we will summarize current learning theories and explore strategies for how to implement these in your classrooms. Most of the time during this session will be spent on this part. During the second part of the session, we will look at strategies for self-reflection. Let's begin with the reflection on the pre-session readings. Which readings are most relevant to you and your teaching, and why? Is there a particular reading that challenged your view of how students learn, and why? First, Think about the answers to these questions on your own for a few minutes. Then, turn to your neighbor and share and discuss your responses to these questions for approximately 10 minutes. Write your individual answers to these questions on the online discussion forum. Pause the video here while you complete this assignment. As you might have guessed already, the pre-session readings are designed to give you a background on the concepts we will be covering in the session. It is important that you complete the pre-session readings as they form an integral part of this course. This session's pre-session readings highlight some key findings and principles that have profound implications for teaching. Mostly, they highlight the need to know and understand how learning takes place so we can design effective teaching practices. In this session, we will highlight 4 questions that are critical to our understanding of student learning. To help our students learn, we need to know and understand how our students construct knowledge, what type of mental models they construct, and how they modify and adapt existing knowledge. We also need to understand what our students know and do not know prior to taking our courses, and how prior knowledge impacts how they learned in our classrooms. In addition, understanding students' mental models and how they differ from those of experts is key. Last, we will look at how course design can affect whether students approach our courses through surface learning or through deep learning. We will now take some time to explore each of these questions, mainly what the research tells us and what practical strategies we can use to translate these into classroom practices. Let's begin by exploring how people learn. In the past 50 years, cognitive and learning science research has truly revolutionized and changed our understanding of how learning occurs. Prior views about learning included the notion that learning is transmitted from the teacher to the student. In this view, the student could be compared to an empty vessel that could be filled with knowledge through teaching. In this view, teaching equals learning. In recent years, this teacher-centered view has fallen out of favor. This has come as a result of our increased understanding of how people learn. Current views about learning argue that students construct their own knowledge. In this view, knowledge is not acquired from the teacher, but rather constructed through the learner's own experiences and reflections. Knowledge is formed when new information gets incorporated into pre-existing mental frameworks, which are based on prior experiences and notions. New information is either readily assimilated into pre-existing mental frameworks or causes their revision. In this view, teaching does not equal learning. We need to invest in strategies that facilitate our students' processes of knowledge construction, which may or may not involve actual teaching. This is one of the critical concepts of this course and will be addressed in more detail in the session on interactive learning and active teaching. The finding that learning takes place through the construction of knowledge by the learner has significant implications for classroom instruction and course design. This means that we, as teachers, should think of ways to support our students with knowledge construction. We can do this through activities that facilitate meaning-making and promote adaptation and revision of pre-existing mental frameworks. To support meaning-making and help students adapt pre-existing frameworks, we suggest 2 different recommendations, as discussed in the pre-session reading titled Applying the Science of Learning by Halpern and Hegel. Vary the conditions under which learning takes place, and facilitate retrieval. Let's explore these two recommendations in more detail. When we vary the conditions in which learning takes place, students associate multiple retrieval cues with key ideas or concepts. This makes it easier for the information to be retrieved. The ability to retrieve information and make use of it in a new scenario or application is called knowledge transfer. Knowledge transfer is what we like our students to be able to do. Without it, our students will acquire knowledge that they're not able to apply to different or novel situations. Nobel laureate Herbert Simon stated, "The meaning of knowing has shifted from being able to remember and repeat information to being able to find and use it." We can change the conditions in which learning takes place through several methods. During class, use both verbal and audiovisual representations of the same concept. Also use diverse examples that illustrate a concept. A concept without examples is difficult to grasp. Examples contextualize the concept and allow learners to be able to separate a concrete illustration, the example, with the enduring, more abstract, transferable concept. Let's say that you explain a particular concept and then provide a single example to illustrate that concept. For the learner who is not an expert in the subject, there's no real difference between the concept and the example. The two tend to merge together in the learner's mind. The learner is often unable to separate the concept from the example. One solution is to provide a second similar example. If an example is similar enough, there will be substantial overlap between the concept in example 1 and the concept plus example 2. This overlap is smaller than a concept and a single example, and the two examples serve to create the boundaries of the concept more clearly. It's even better to provide a third example that is distinct from the first two. This helps students differentiate the overlap between concept and examples. The concept stands out more clearly. Another useful way to vary the conditions in which learning takes place is to provide students with opportunities to represent the information in an alternative format. For example, you can ask your students to describe and explain in words the concepts they have learned through mathematical equations, or vice versa. Ask students to visually, through a diagram, represent descriptions of concepts, reactions, etc. Learning and retrieving is enhanced when students are asked to retrieve and integrate information both verbally and visually. As we have previously mentioned, knowledge transfer is the consequence of understanding or deep learning, learning that is really understood and can be applied. As Halpern and Hegel reminds us in the Applying the Science of Learning pre-session reading, we need to always remember that we are teaching towards some time in the future when we will not be present, and preparing students for unpredictable real-world tests that we will not be giving, instead of preparing them for the traditional midterm and final exams. Long-term retention and transfer can be achieved through retrieval and application. The strength of the memory trace or the connections in the brain made through the process of remembering and eliciting information becomes stronger each time a student is asked to retrieve the same information, particularly if they are asked to apply the information in new, novel ways. There are many ways in which you can ask your students to retrieve information or concepts. One strategy you can use is to ask your students to explain to each other their answer to a question or problem. As we will see in the session on interactive teaching and active learning, this strategy can result in higher learning gains and increase student attention. Asking your students to respond to questions or solve problems on a particular concept even after it has been taught can also facilitate retrieval. Spacing the retrieval opportunities so that the time interval between opportunities increases is preferable to constant retrieval for a short amount of time. Instead of always asking students to retrieve something right away, vary the time between presenting the concept and asking them to retrieve it. This allows for concepts to be integrated into existing frameworks more robustly and for those connections to deepen over time. As we have already mentioned, applying knowledge to new situations leads to transfer, whereas applying the learned knowledge to similar situation only results in memorization. Therefore, don't just change a few variables within a problem, but instead provide your students with substantially different problems that illustrate the same concept. Now, let's take a look at how understanding what students know before taking our courses can transform our teaching. Learning research indicates that the single most important determinant influencing students' learning is how much students already know and what they know prior to taking our courses. Rather than being blank slates, students enter the classroom with personal notions about how the world works, which are determined by previous classes, personal experiences, the media, peers, family, etc. Some of these notions might contain faulty logic or misconceptions. When students come into our classrooms and encounter new information, they have to reconcile it with their own previous ideas and notions. Research on misconceptions has shown that once these faulty ideas take place, they're very persistent and difficult to change. Given the importance of prior knowledge on learning, understanding what students know is key for effective instruction. This can be accomplished in different ways. You can start by assessing knowledge and understanding at the start of each course, probing for conceptual understanding. This will allow you to know the knowledge base of our students, including what they already know and what they have difficulty with understanding. You can then provide the same test several times during the duration of your course and at the end of the course to continue to probe for understanding. As an added benefit, administering a pretest can also help diagnose which students might be at danger of not passing your course and be able to advise them on the resources and strategies available. Pretests come in various shapes and sizes. You can certainly design your own using questions that you have developed in the past. There are also several published and validated pretests for undergraduate education called concept inventories that are available for many disciplines. Another strategy for determining prior knowledge is to use in-class concept questions. These questions are designed to expose common difficulties in understanding and misconceptions and can require problem solving. Here's an example of a concept question relevant to introductory biology. The majority of actual dry mass gained by plants as they progress from seed to adult plants comes from which of the following substances? A. Nutrients in soil that are taken up by plant roots. B. molecules in the air that enter through the holes in the plant leaves. C, water taken up directly by plant roots. And D, energy from the sun. Pause the video here and take a moment to think about the answer to this question. The correct answer to this question is B, molecules in the air that enter through the holes in the plant leaves. 80 to 90% of a plant's overall mass is water. 96% of the dry mass is organic substances such as cellulose and proteins. The plant absorbs carbon dioxide through its leaves, and through photosynthesis, the carbon dioxide is combined with hydrogen atoms from water to form sugars that are the basic components of cellulose and other proteins. This makes up the majority of the dry mass. The energy from the sunlight is converted into chemical energy and helps catalyze critical reactions during photosynthesis, but energy itself is not converted to mass. As you can see, this question is designed to document a common set of misconceptions in biology: that nutrients in the soil taken up by the roots make up most of the actual mass of the plants, or that the energy from the sun's energy is directly converted to dry biomass. When this question was given to introductory biology students at Michigan State University, only 4% of the students chose the correct answer. Questions such as this one can be designed for every class and given throughout the semester to document what students know. In the session on interactive teaching and active learning, we will discuss ways in which concept questions can be utilized to introduce small group activities and active learning during class time. Another recommendation for determining what students know is the use of mud carts. What are mud carts? MUD, M-U-D, stands for muddiest point. Mud carts are provided at the end of each class and typically contain 1 or 2 questions, such as, what was the muddiest point in class today? What remains unclear to you? What other comments do you have about today's session? Mud carts can be incredibly useful at documenting what concepts are difficult or what was not clearly explained during class. And they're very useful at uncovering faulty thinking and logic. Also, answers to common questions written by students on the mud carts can be addressed in the first few minutes of the next class. It is important to remember that for students to value filling out mud carts, it is necessary to make sure that you as a teacher take time to address their questions and difficulties. In this course, we will be asking you to fill out a mud cart at the end of each session. Answers to your questions will then be addressed through the course website before the next session. Now let's talk about how understanding the differences between novices and experts can have profound impact for our teaching. Studies probing the differences between how novices and experts organize knowledge have revealed that experts' knowledge is not a list of facts and formulas, but rather that their knowledge is organized around core concepts or ideas. This results in the division of knowledge into interrelated chunks, which allows experts to select relevant knowledge from a vast knowledge repository easily and efficiently. Let's use an example to demonstrate this finding. In this particular study, a chess master and a Class A player, which is a good player but not a master, and a novice player were given 5 seconds to view a chessboard positioned from the middle of an actual game. After 5 seconds, the board was covered and the study participants were asked to recreate the board positions from memory. This was repeated several times to allow participants to eventually get all the positions correctly. Plotted in this graph is the number of trials versus the number of pieces correctly recalled. On the first trial, the master player correctly positioned more pieces than the Class A player, 16 versus 8, and correspondingly, the Class A player correctly placed more pieces than the novice player, 8 versus 4. However, these differences in performance only occurred when the board was arranged in a meaningful way. When chess pieces were randomly arranged on a chessboard, then the number of pieces that were correctly placed on the board after one trial by the master, Class A, and novice players was the same, approximately 3 pieces. This example demonstrates that the process of making hierarchical mental models organized around core concepts or big ideas allow experts to see patterns of meaningful information that novices cannot. The other aspect of expert performance that is demonstrated in this chess example is that experts have superior recall of knowledge, which surpasses working memory's limitation. As we will explore in more detail in the session on preparing and presenting a lecture, there are limits to what people can hold in working memory. By organizing information into meaningful chunks, experts are able to surpass the limits of working memory. This is known as chunking. Novices, on the other hand, lack hierarchical, meaningfully organized mental frameworks and are therefore not able to take advantage of chunking. Additionally, novice knowledge is compartmentalized and rigid, making retrieval, real understanding, and knowledge transfer very difficult. In contrast, expert knowledge is flexible and highly interconnected. They do not have to search through everything they know to find the relevant information for a particular problem. A strategy for implementing these findings is to demonstrate how experts think and approach problems. This facilitates the evolution of expert thinking in our students. Keep in mind that students will still need to make sense of knowledge on their own, as we have previously mentioned, but making expert thinking transparent will facilitate the development of expert thinking over time. As we have already discussed, experts are particularly good at retrieving information relevant to the task at hand. For knowledge to be easily retrievable, it should be conditionalized. That is, we should know under which circumstances the knowledge is useful and why. Knowledge that lives in a vacuum is hard to retrieve. Traditional curriculum often fails to demonstrate to students the when and where and whys of using specific knowledge. Therefore, one of the recommendations for this strategy is to provide students with examples of when specific concepts, formulas, laws, etc. should be used and why. Another recommendation for facilitating expert thinking is to make relationships among an idea or concepts explicit. This applies to both instruction and evaluation approaches. For example, structure and organize your curriculum so that the connections between the concepts is clearly described. Refer to prior lectures and show how knowledge covered in prior lecture connects with current knowledge. Ask students to build a concept map. Concept maps are diagrams that illustrate how concepts relate to one another. When building concept maps, students identify the concepts learned and organize them into hierarchical schemes. In this example, a concept map is used to explain the seasons. Concept map variables used to explain why we have seasons are placed inside boxes and are organized in a hierarchical manner, with the most inclusive and general variables at the top of the map and the most specific, less inclusive variables below. Another important characteristic of concept maps is that the relationships between the different variables are indicated with arrows, and the nature of these relationships is shown with labels. Notice that some variables can be connected to more than one other variable. This cross-linking demonstrates rich interconnections that characterize deep understanding. Concept maps are extremely effective tools for learning because they provide opportunities for students to build and revise mental frameworks and model the process of building mental models that experts develop through years of experience and practice. Another strategy is to model how an expert approaches and solves a problem. Studies in physics, mathematics, history, among other disciplines, have demonstrated that experts approach problems carefully, first thinking about the particular concept or idea that is involved in the problem. In contrast, novices try to use surface features about the problem, such as the language and type of variables defined, to search for the correct formula or analysis to apply. This results in an inability to apply knowledge to unknown situations. Let's explore the following example that demonstrates how experts and novices differ in their approaches to problem solving. In this study, novices and experts were asked to group physics problems based on solution types. Novices tended to categorize problems based on similar surface features. For example, the two different problems shown here were placed on the same category by novices because both have blocks on inclined planes. On the other hand, experts tended to categorize problems based on the major concept that can be applied to solve the problem. In the example shown here, experts justify the categorization of two seemingly different problems because they both demonstrate the concept of energy conservation. Therefore, when solving problems in front of students, take time before you begin to state and explain your approach. Reveal to your students the sequence and nature of thought processes that take place in your mind when solving problems. In addition, when you ask students to solve problems, also ask them to justify their particular approach. Course design has a lasting consequence on learning. What we decide to cover or not cover in our courses, for instance, can influence the approach that students take to learning. Courses that cover too much content leave little time and room for students to organize knowledge meaningfully. There is not enough time to cover concepts in depth. When breadth is emphasized over depth, the highly rich and contextualized mental frameworks that characterize deep understanding cannot be built. Without connections, knowledge exists mostly in the context in which it's learned. This leaves students with the inability to transfer concepts to novel situations. Therefore, structure your course so there's a greater emphasis on conceptual understanding rather than the amount to be covered. To accomplish this, start by thinking about the seminal concepts that you would like your students to be able to know and demonstrate by the end of the course. This process is called backward design, and we will cover in depth during the session on creating a course and constructing a syllabus. Backward design leads to the prioritization of content, which will facilitate your ability to cover fewer concepts more deeply. Design assignments and assessments that emphasize deep understanding and encourage students to approach the subject as deep learners. If during our lectures we emphasize conceptual understanding, but our assignments and exams do not require students to think deeply, then our students will tend to approach the subject as surface learners. In the session on constructing effective problem sets and exam questions, we will demonstrate how to design questions that encourage deep learning and critical thinking skills. Now that we have had time to explain strategies for implementing current theories on learning, think first on how you will implement at least 2 of the learning theories covered in the pre-session readings and in today's session. Then, identify and describe specific activities or assignments that you would implement and explain how they are supported by the research findings and learning theories. Work first on your own for 5 minutes. Then, discuss your answers with your immediate neighbor. Provide a description of the strategies and activities or assignments that you identified in this activity on the course's online forum. We have discussed how learning research can inform your teaching and course development. Now, let's discuss some of the strategies that you can implement to document and reflect on whether your efforts implementing these strategies have worked. As we have previously mentioned, mock cards can provide student feedback on individual sessions and can show you whether your teaching strategies and course design seem to lead to increased understanding. In addition, they can clarify what is difficult for students to know and do, and identify misconceptions that might deserve more attention. At the end of each class, take a few notes on what you think worked and did not work. These notes can help you modify the sections and approaches that did not work so well. Ask a fellow instructor to come and observe one of your lectures and give you constructive feedback. Lastly, at the end of the course, spend some time thinking and documenting what you think worked and what you think did not. Be sure to look at the course design, teaching behaviors, and instructional strategies and assessment materials. The implementation of these reflection strategies will provide a rich set of data which you can then use to improve your own future teaching and courses. In this session, we discussed strategies for implementing learning science research findings to improve our teaching and increase student understanding. Specifically, we discussed how understanding how people learn can allow us to support our students' ability to construct meaning. We also discussed how prior knowledge is the most important factor for how and what students learn. Knowing what our students already know allows us to adjust our teaching and address misconceptions more effectively. We looked at how experts and novices differ significantly in their approaches to problem solving. Experts organize hierarchical mental frameworks allows them to easily retrieve and apply information to new contexts. Illustrating expert thinking can allow your students to consciously emulate expert problem-solving strategies. Lastly, we explored how incorporating strategies for reflection will allow you to make conscious changes to improve your teaching and courses. Do you have any questions or comments? Take a moment to write lingering questions or comments that you might have on the discussion forum now. In the post-session assignment worksheet on the course website, there's a table with 8 findings about how people learn. Choose 4 of the 8 findings and 1. Write a short description of the finding, and 2. Provide examples of how you have used this finding in your teaching or could use it in the future. Please see the instructions on the course website for information regarding the submission of your assignment. Immediately following your viewing of the session, please follow the link to the online survey for the mud card.